Hello everyone, my name is Akanksha Chaudhary and today I will be presenting the work I did as part of my final year undergraduate thesis at BITS Pilani, Goa, India, under the guidance of Professor Sanjoy Barua at Washington University in St. Louis, USA. In this work, we will be discussing the efficient schedulability analysis of semi-clairvoyant sporadic task systems under the assumption of graceful degradation within the broader context of real-time scheduling theory. Recent advancements in computational frameworks for real-time embedded systems are primarily being impacted by two trends. First, such frameworks are becoming increasingly complex in order to deliver high performance. And second, there is an increasing pressure to host such systems using platforms that require less weight, small volumes, and low power. Motivated by these trends, most of the complex real-time embedded systems are now evolving into mixed criticality systems. A mixed criticality system allows consolidation of components with two or more distinct levels of criticality onto a common hosting platform. Here, the term criticality refers to the level of assurance against failure. As a means for attaining timing predictability in such systems, Vestil proposed an abstract behavioral model for mixed criticality workloads. In this model, individual segments of real-time code are modeled as schedulable entities called jobs. Each job, Ji, has an arrival time, Ai, deadline, Di, and a criticality level, Chi, associated with it. In this presentation, we will be restricting our attention to dual criticality systems with two distinct criticality levels, low and high. For mixed criticality workloads, the worst-case execution times, or WCETs, of its jobs depend on their criticality parameters. Therefore, the Vestil model specifies multiple different estimates of the WCET parameter for each job, one corresponding to each criticality level. Now let's take a look at the runtime behavior of the model we've just described. At any given time, the system can either be in the low criticality mode or the high criticality mode. A system typically begins its execution in the low criticality mode. If at any point in time a job in the system exceeds its low criticality WCET bound, as shown in the diagram, a mode switch from low criticality mode to high criticality mode is signaled at runtime. Therefore, in order to determine the schedulability of a system over a given time interval, we need to know which of the two WCET parameter values apply at each point in time. Depending on how and when this information becomes available to the system, different forms of clairvoyance have been identified for mixed criticality scheduling models. Most of the prior works on scheduling theory have discussed clairvoyant and non-clairvoyant models in the context of mixed criticality systems. In a clairvoyant scheduling model, it is assumed that the precise values of actual execution times of jobs are known beforehand, that is, prior to any job arrivals. However, due to the unpredictable variations in actual execution times of jobs, it is difficult to determine their precise values before runtime. Therefore, such a model is essentially an idealized abstraction that is highly unlikely to exist for a practical system. A non-clairvoyant scheduling model, on the other hand, assumes that no information about the actual execution time of a job is revealed before its completion. In this case, which of the two WCET estimates of a job apply during a particular execution can only be determined by allowing the job to execute either until it terminates or until it has executed for a duration equal to its low criticality WCET bound. So if any job in the system signals a high criticality behavior, it is only known at runtime when the job signaling this behavior has already executed for a duration equal to its low criticality WCET bound, as shown in the figure. Since actual execution times for realistic systems are typically unknown, most of the prior work in mixed criticality scheduling theory assumes a non-clairvoyant scheduling model for performing the timing analysis. Recently, however, another intermediate form of clairvoyance, termed semi-clairvoyance, was introduced for mixed criticality systems. In this model, it is assumed that each job reveals upon arrival which of its WCET parameters it will respect. That is, whether the execution time of the job exceeds its low criticality WCET or not. Note that the precise value of the actual execution time is not revealed. So, if the execution requirement of any high criticality job in the system exceeds its low criticality bound, a mode switch occurs at runtime, at the time instant of its arrival. A semi-clairvoyant model is particularly beneficial for modeling mixed criticality systems in which execution times of jobs depend on the system's state. For instance, if in a system alternative implementations of the same job are provided, say each corresponding to a different mode of operation, then which of the provided implementations would be the appropriate one to execute is presumably better known at runtime, when the job arrives. Recent works also demonstrate that a semi-clairvoyant model provides significant quantifiable benefit over the conventionally considered non-clairvoyant models in terms of speed-up factor and schedulability. More recently, the problem of graceful degradation has been considered in the context of semi-clairvoyant scheduling. Multiple different notions of correctness for graceful degradation have been proposed. Consider a scenario where a high criticality job Ji signals a mode switch upon arrival. Once the mode switch is signaled, all jobs arriving at or after this instant are permitted to require up to their high criticality WCTs, and all the high criticality jobs arriving at or before this are permitted to require up to their low criticality WCTs. This is because they haven't signaled a high criticality behavior. But what about the low criticality jobs that are active at the time of mode switch? Based on the service guarantees provided to these jobs, three different notions of correctness have been defined, referred to as correctness criteria CC1, CC2, and CC3. Under the correctness criterion CC1, all low criticality jobs that have deadlines after the mode switch instant may require up to their smaller high criticality WCTs. Under the correctness criterion CC2, all low criticality jobs that begin execution after the mode switch instant may require up to their smaller high criticality WCTs. And under the correctness criterion CC3, all low criticality jobs that arrive after the mode switch instant may require up to their smaller high criticality WCTs. For each of these notions, efficient scheduling algorithms capable of ensuring graceful degradation have been derived as shown in this table. Interestingly, EDF was found to be an optimal scheduling algorithm for both independent jobs and sporadic tasks under CC3. Exact schedulability tests are derived for both these cases. Placing and comparing all of these results in a broader context, the authors recommend that CC3 be considered the default correctness criterion and EDF be considered the default runtime scheduling algorithm for semi-clairvoyant scheduling. In this paper, we study the exact schedulability test for semi-clairvoyant scheduling of arbitrary deadline sporadic task systems under the default correctness criterion, that is CC3. The existing analysis for the problem considered in this work determines the schedulability of a system using processor demand analysis. This technique uses per-task demand-bound functions to calculate the maximum cumulative execution requirement of the system over a specified interval length. If the cumulative execution demand over any interval exceeds the interval length, then the system cannot be scheduled by preemptive uniprocessor EDF. Otherwise, the system is deemed schedulable. In order to guarantee the schedulability of a system in all cases, it suffices to guarantee its schedulability for its worst-case behavior. In this case, the worst-case behavior is realized when the cumulative processor demand of the system is maximized. Let's consider an interval length of t in which a mode switch is first signaled as 10 minutes into the interval. Then, for our problem, the worst-case scenario occurs when a maximum number of low criticality jobs are released before the mode switch instant so that they require up to their larger low criticality WCETs. This corresponds to the case where a job is released at the start of the interval and all the subsequent jobs generated by the task are released as early as possible. The worst-case scenario for a high criticality task is realized when a maximum number of its jobs are released after the mode switch instant so that they require up to their larger high criticality WCETs. This corresponds to the case where a job has its deadline at the end of the interval and all the previous jobs generated by the task are released as late as possible. For this case, the demand-bound functions for low and high criticality tasks can be calculated using these expressions. Each term in the expression multiplies the number of jobs that have arrival times and deadlines within an interval with the maximum permissible execution budget for that interval. The cumulative processor demand of the entire system can then be determined by summing up the demand-bound functions obtained for all the individual tasks. The schedulability of a sporadic task system can then be determined by checking the cumulative processor demand of the system for each interval length t belonging to the set 0, 1, 2, all the way up to the upper bound b, considering all possible mode switch instance s in S of t. The expressions for b and S of t have been derived by Barua and Ekberg in their paper Graceful Degradation in Semi-Clairvoyant Scheduling. These can be calculated using the task set parameter values. So the test proceeds by checking the cumulative processor demand of the task system over each interval length in an increasing order starting from 0. All possible mode switch instances are considered for each interval length. These cases are depicted by red arrows in the given figure. If for any combination of t and S in S of t, the cumulative processor demand exceeds the interval length, the task system is found to be not schedulable. If the condition is satisfied for each interval length t, considering all possible mode switch instance S and S of t, the task system is deemed schedulable. However, note that in order to determine the schedulability of the system, the cumulative processor demand needs to be calculated pseudo-polynomially many times with respect to b. So in order to determine the schedulability of a system using the given test, we may have to check up to floor of b plus 1 number of interval lengths. And for each interval length t, all possible mode switch instance s belonging to S of t would also need to be checked. In practice, for many systems, the computed value of b and hence the number of TS pair point combinations for which the processor demand needs to be checked can be quite large. By needing to iterate through all such points, a significant amount of time and effort would be required to determine the schedulability of such systems. In this work, we attempt to address this issue by proposing mixed criticality quick processor demand analysis, or MCQPA, as a faster and practice way to implement the exact schedulability test. MCQPA is based on the quick processor demand analysis, or the QPA strategy proposed by Zhang and Burns. The main idea behind processor demand analysis is to check the cumulative demand generated by the system for each interval length. QPA speeds up this process for a conventional real-time sporadic task system. Instead of considering all interval lengths in an increasing order as is done in the traditional implementations, QPA does so in a decreasing order, starting with an upper bound and progressively iterating downwards, safely skipping some interval lengths as it moves towards an interval length of 0. But how does this work? In order to safely skip through the interval lengths, QPA exploits a critical insight that the cumulative processor demand, denoted here by dBf of t, of a conventional real-time system is monotonically non-decreasing with respect to the interval length t over which it is calculated. So for any t prime less than t, we have dBf of t prime less than dBf of t, or dBf of t prime equals dBf of t at most. Using this insight, QPA can safely skip through all interval lengths between t and dBf of t. So the next point that needs to be checked is t prime equals dBf of t. Unfortunately, this insight cannot be applied to our problem directly because we need to consider the cumulative processor demand dBf t, s multiple times, once for each s in S of t, for a given interval of length t. We thus derive some properties of the demand-bound functions that will let us formulate a modified QPA strategy that is indeed applicable to semi-clairvoyant schedulability analysis. The first property establishes that the processor demand dBf t, s is monotonically non-decreasing with respect to the interval length t for a given s point in 0 to t. This property is then used to prove another property which states that the maximum cumulative processor demand that can be obtained over a given interval by considering all possible mode switch cases is monotonically non-decreasing with respect to the interval length t. This property, that is analogous to the insight exploited by QPA, therefore helps us formulate a more efficient test called MCQPA for semi-clairvoyant mixed criticality scheduling. In order to determine schedulability, MCQPA considers interval lengths in a decreasing order, starting with the predetermined upper bound B. The algorithm then computes the cumulative processor demand for all possible mode switch instance S belonging to the set S of B, depicted by red arrows in the figure. The maximum cumulative demand seen is recorded for this interval length. Once it is determined that this demand does not exceed the length of the interval considered, property 2 allows us to conclude that the maximum cumulative demand of the system over any interval length t prime that is greater than this value will never exceed t prime. Hence, the interval length t is updated to the maximum cumulative demand obtained in the previous run, safely skipping over all the points in between. In this manner, we continue iterating downwards progressively until we reach the interval length of 0. Thus, the essential difference between the two approaches is in the number of interval lengths that are considered. While the prior approach needs to consider all the integer valued interval lengths up to b, MCQPA can skip through some of those interval lengths. How many interval lengths are skipped, and does it even matter? In order to examine this, we experimentally evaluate the effectiveness of MCQPA over the prior approach via simulation upon synthetically generated workloads. The methodology used to generate the workloads is described in section 5.1 of the paper. The experiments are conducted for 3 different criticality proportion values that are 0.25, 0.5, and 0.75, representing a lower, equal, and a higher percentage of high criticality tasks in the workloads, respectively. The utilization values are varied from 0.1 to 0.9 in each case, and simulations are carried out for 200 task sets, each containing 20 tasks. We now present the outcomes of our simulation experiments. The 2 plots shown here record the number of interval lengths and TS pair points checked by both the algorithms for different CP values. We see that the prior approach is required to check a very large number of interval lengths and TS pair points varying in the ranges of 10 power 5 to 10 power 7 and 10 power 5 to 10 power 8 respectively, whereas MCQPA only needs to check a considerably small fraction of these numbers, that is, around 10 power 2 to 10 power 4 interval lengths and 10 power 2 to 10 power 5 TS pair points. In order to examine the speedups achieved in each case, we introduce the coefficients alpha and beta, where alpha records the relative speedup achieved by MCQPA in terms of the number of interval lengths checked, and beta records the relative speed in terms of the number of TS pair points checked. Note that beta here gives a finer grain measure for the actual work done by the 2 algorithms. From the graphs shown in this slide, we observe that MCQPA is about 1,000 to 10,000 times faster for task set utilizations lower than 0.7 and about 10 to 1,000 times faster for task set utilizations greater than 0.7. Note that a steady increase in the speedup coefficient values is seen for task set utilizations less than or equal to 0.7. This can be attributed to a larger value of the upper bound B that is obtained for these cases, because of which the number of interval lengths and therefore the number of TS pair points that need to be checked by the prior approach increase significantly, whereas MCQPA can skip through most of these. The sharp decline in the speedup coefficient values for higher criticality utilization is because as the task set utilization increases, the schedulability of the task sets decreases considerably. This reduces the number of interval lengths and therefore the number of TS pair points that need to be checked by the prior approach, while MCQPA more or less checks the same number of interval lengths and TS pair points. However, note that even for higher task set utilizations, MCQPA can achieve a speedup of about 10 times even in the worst case. Hence, our evaluations provide convincing evidence that MCQPA significantly outperforms the prior approach over a vast range of system characteristics. So, to summarize, in this paper, we consider the problem of semi-clairvoyant scheduling of sporadic task systems with graceful degradation. We then propose and prove correct MCQPA, more efficient, exact schedulability test for this problem. Finally, we present an experimental evaluation of MCQPA demonstrating its enhanced effectiveness in determining schedulability over prior approaches. Thank you.